This is the first video for the lecture Introduction into PDE. Here you see the organization of this lecture. This lecture has 5 chapters. In the first chapter we consider, this is a preliminary chapter, we consider first order PDEs. We will see that first order PDEs really differ from higher order PDEs. So we start as a warm-up with the simplest PDE, namely the homogeneous transport equation. This later we will need this. Okay, so the homogeneous and the inhomogeneous transport equation. These are our first examples. Then we obtain another example of a first order PDE, and we will meet some problems of this general method which applies to all these first order PDEs. And this general method will be finally introduced in the last section of the first chapter. There we consider general first order partial differential equations. Okay, so but in section 1.3 we will meet some problems, and in some sense we see how to overcome this. This first chapter should be a motivation for general concepts which we then introduce in the second chapter. And the second chapter should be itself considered as a preparation for the final 3 chapters. Because after the second chapter we consider the main 3 examples of second order PDEs. And these main 3 examples are the Laplace equation, the heat equation, and the wave equation in chapter 5. Chapter 4 and 5 are not yet translated. I hope to do so. Presumably these chapters 4 and 5 will be later also in English. So after this introduction in section 1, this preliminary introduction where we introduce the first order PDEs, and we find some general method finally to solve such first order PDEs. We will understand in the second chapter that PDEs in general don't have a solution. So there doesn't exist a general method to solve PDEs. This is really different from ODEs. And so we start with this in the second chapter by some very important theorem, namely the divergence theorem, which is generalization of the fundamental theorem of calculus to higher dimensions. This we will see several important consequences of this theorem. In the first section we only present 2 of them. We will understand why this scalar conservation laws are conservation laws, namely what are the conserved quantities. We will see, and what is the meaning of a conserved quantities. How to formulate a conservation law. This depends on the divergence theorem. Here we only do it in 1 space dimensions, and here we do it in general. Then we introduce classification of second order PDEs, and then we give an example of a PDE which does not have any solution. It has smooth coefficients but doesn't have any solutions. And then, since we already saw in chapter 1.4 that there exists some reason to think about more general solutions, we introduce the concept on which all generalizations, more or less all generalizations of solutions depend, namely distributions. And these 2 sections, they are very short. There we just introduce general concepts, the concept of regularity and boundary value problems. Yeah, these are two concepts which will turn out to be very important for general PDEs. And then afterwards we shall focus only on second order linear PDEs, and we will restrict ourselves to the three main examples. Yeah, in section 2.2 we already understand in which sense they represent typical examples. Okay, so this is the total program. So let's start now with chapter 1. But before we really start with first order PDEs, we first define what is a PDE, what means to be a PDE. And here we have written a general PDE. Yeah? Okay, so what means PDE? It's an equation in which we insert the values of a function and its derivatives. Yeah? So in contrast, of course, in analysis and linear algebra, you have met equations which describe some problems, and you look for solutions of these equations. And typically, this solution were numbers or vectors. Yeah? You look for vectors which solve some problems. Here it's different. Yeah? For a partial differential equation, the unknown function, the unknown object, is a function. Yeah, and here in this situation, also it's very typically, that this is just a convention, that in the theory of PDEs, this unknown function is always called u. So u is a function on some set omega, and it is a real valued function. It might also go to Rn, yeah, somewhere. But in this lecture, it's really real valued, yeah, and omega is a subset of Rn and open, yeah, very important for us. We have open subsets of Rn, yeah, and n is larger than 1. Why? Yeah, because if it would be only one-dimensional, then we would call this an ODE, an ordinary differential equation, because then it would involve only derivatives with respect to one variable. Okay, and now what does this expressions mean here? Yeah, so du is a function from omega to Rn, and in this situation here, which is just the gradient. Yeah, so du of x is the first partial derivative of x, and so on until the last partial derivative. Yeah, so, and we write this as a vector, so I put this in brackets. Okay, so du just stands for all first order partial derivatives. Okay, now d2 u omega 2, and now, okay, now we take all second order partial derivatives. So we can arrange this in a matrix, n by n matrix. Yeah, I write this in this form. This should be considered as an n by n matrix, so it has n square components. Yeah, n square components. And okay, and what are the components? Let me abbreviate d by dxi as di. Yeah, then then it's d1 square u of x. Yeah, okay, let me also let me don't write the argument, just the function. Yeah, so first order partial derivative, also the d by dx square. Okay, and then the next term is of course d2 d1 u, and so on, and then the last term is dn d1 u. Okay, what is in this is the first row of this matrix. Now what is the second row? This is of course d1 d2 u, d2 square u, and so on, dn d2 u, and so on, and finally we have d1 dn u, d2 dn u, and dn square u. Okay, we see these are all second order partial derivatives. Yeah? All second order partial derivatives. Yeah, this d2 stands for, yeah, all second order partial derivatives. Okay, let's think a little bit on this. Are they really independent? Are they all independent? And as you should know, yeah, from analysis 2 or from former lectures, if u is twice differentiable, then second partial derivatives commute, yeah, by Schwarz theorem. Then di dju is the same as dj diu. Yeah? Second, so they are not independent. Yeah? Only all these entries in the upper triangular, including the diagonal, they already complete everything. Yeah? In case that u is twice differentiable. But this we will always assume. We will always assume that for a solution, yeah, we assume that the function is as many times differentiable as the highest order of a partial derivative which shows up. Yeah, so in this example, k is the order. K is called order. K is called order of the PDE. Here in this example, yeah, in our script in definition 1.1. Yeah, in definition, 1.1. Okay, so now we understand this. This has quite many entries. Now dk is the vector, yeah, is the combination of all partial derivatives of order derivatives of order k. Okay, so we see the higher here this exponent comes, also this exponent at the d becomes, the more entries this has. Yeah. Okay, so this grows with the entries, and so this is a function which really depends on quite a lot entries. Yeah? So I don't make this explicit because it can be also a vector valued function and so on. U can be a vector valued function. Yeah, then maybe we would speak about systems of ODE, and yeah, this is a general form. Yeah, but observe, yeah, the equation in definition 1.1 is not completely general, in the sense that it's an arbitrary equation which combines values of partial derivatives. What is not general? Yeah, all derivatives. This is are evaluated at the same point. Yeah, here you see we always insert the same point x in our domain of our unknown function. Okay, yeah, so here of our unknown function u. Yeah, this is so whenever one speaks about a partial differential equation, this means a PDE, let's recall this, is therefore always, yeah, this is always an equation on the values of an unknown function and the derivatives of the unknown function at one point. Yeah, we all evaluate this at the same point. Yeah, this is always the case for it. But this is more or less the only restriction. Yeah, otherwise it can be completely general. Okay, typically we assume that we only have finitely many different derivatives. Now, I already introduced this partial differential equation. Now, how we abbreviate higher order derivatives. Higher order derivatives are abbreviated by d gamma. Now here gamma is a multi-index in natural numbers including 0 to the power of n. Okay, and then d gamma u, what does this mean? This means d1 to the power of g1 until dn to the power of gn of u. This order here, this doesn't play a role. Order does not play a role if u is as many different is G, which is the sum of the orders. Yeah, this we call the order of K, or the weight. So yeah, we abbreviate the sum of all this in if n is n times differentiable. Again, since then all the derivatives commute. Yeah, so in this sense, in this situation, this doesn't depend on this order. Yeah, of course we may. Yeah, so that we write it this way is just one way. We may write it also differently. Okay, now comes the first exercise, generalized Leibniz rule. Yeah, I think you should know from analysis 1. Of course, you know the Leibniz rule. Also for functions depending on a real variable x, there we have if fg prime, this is the Leibniz rule, is fg prime plus fg prime. Yeah? This you know. Okay. Yeah, and there exists a generalization, yeah, by induction. This implies that if we take the nth, we already fixed, so let us call it k, the kth derivative, and this is now a sum, e equals 1 to k times this binomial coefficients, k over I times g, sorry, gn minus I. Yeah, by induction, also presumably you have seen this formula. Yeah, and now by further induction, one obtains this formula. Yeah, so this is an exercise. Yeah, so maybe if you don't know this, and if you can try, it's not so difficult. Yeah, it's not so difficult. You just have to remember the definition of this coefficients. Yeah, maybe I recall this coefficients. This is of course, this is k faculty divided by e faculty times n minus e faculty. Yeah, and 0 faculty is 1. Yeah, so this is the definition, and I is smaller or equal. Okay, so yeah, and also if you don't try to solve this, it's really not difficult, just by induction. Maybe you first look for second order, and then and if you understand this, then this induction is more or less the same. Yeah, so this is not so difficult. Nice exercise. Okay, so this finishes now our preliminary introduction into PDEs. What are partial differential equations, and some notations. And now we start. With the first example. And the first example is the homogeneous transport equation. Yeah, here it's written. So u, the unknown function. This is this is in this situation a function on the Cartesian product, a real function, yeah, and of Rn with R, and the elements we denote by Rn cross R. So x is a vector in Rn as before, but in addition we have t, and t typically stands for time. So this is the time. Okay, and whenever we have such a situation, we also will meet in the heat equation and in the wave equation later. Yeah, so this will show up in more situations. And whenever we have such a function, let's assume it's differentiable, then u dot is just du by dt. This is just a definition. Yeah, u dot is defined as du by dt, and of course the gradient of u is just a vector of first order partial derivatives with respect to x. Yeah, so we write du by dx1 until du by dxn. Yeah, of course, in general, they will depend on x and t. Okay, so now we have, and b is a vector. Yeah, also is any vector. Also, of course, maybe we should restrict to the case that it's non-zero. Otherwise, the equation is not really interesting. Yeah, also any vector. Then we have here such a partial differential equation. Yeah, maybe I write it more explicitly. X of t u dot plus gradient u of x of t. This is so du by dt of xt plus first b1 du by dx1 of xt plus bn du by dxn of xt. Okay, this is how this looks like here. Yeah, and the equation is that this should be 0. This is our equation, and now we want to solve this equation. Yeah. Later in section section 1 point, I think it's 5. Yes, in section 1.5. Yeah, also in section 1.5 we present a general method how to solve quite general first order PDEs. Yeah, and this method will depend on the choice of such a function along some trajectories. Yeah, and in this situation, the trajectories we choose, yeah, choose trajectories. Yeah, for xt in Rn cross R. Yeah, and we choose them in such a way that S goes over at S equals 0. It should be at this point. Yeah, and so we have it x plus s times b and t plus s. In this way we choose it. Yeah, you will see in a minute why it's reasonable to choose such a trajectory. And then maybe I draw, yeah, here time and here x, also for one dimension we can draw this, and then we have here some point, and then yeah, and if we also draw here S, so this moves in some direction, yeah, this coordinates, and here is T and here is X, yeah, for S equals 0. So this is a line, and the derivative is just B, yeah, the slope is just B, yeah, so we choose such a trajectory, and now we calculate the derivative. Also define function set of S as the value of our unknown function x plus s times b t plus s, and we assume that the unknown function is a solution. For any solution of the transport equation, yeah, I abbreviate this as T, transport equation. Okay, so we define this now, and since we have given a differential equation, it's natural. Now, okay, this is a real function, yeah, a function set goes from real values to real values. S maps to u of x plus sb and t plus s. So we just consider the values of our solution, which might be any solution, along such a line for fixed x and t. Now, of course, let's calculate the derivative, z prime of s. How one can calculate the derivative? Now, what rule we should use? Maybe you try for yourself to calculate this, yeah, and stop the video and try to calculate this, please. Yeah, now I will present the solution. Yeah, now this is an inner function. We have an inner function S. Yeah, the answer is one should use the chain rule. This is x plus sb, t plus s. This is an inner function. And u, this is x plus sb, comma t plus s, going to u of x plus sb, comma t plus s. This is the outer function. Okay, how one calculates the derivative of such a composition of two functions? Yeah, observe. This is a function going, the inner function, yeah, this goes from R to Rn cross R. And the outer function, this goes from Rn cross R to R. Okay, such a function. How looks the derivative, or what is the derivative? Yeah, we take also chain rule. What tells us the chain rule? It tells us the derivative is the product of the Jacobi matrix. Yeah, the derivative z prime of s is the product of the Jacobi matrices. And in which order? Yeah, it should be the derivative of u. This is on the left, yeah, also first, this means, yeah, since from linear algebra, you know, the matrix which comes first stands on the right hand side. the Jacobian of the inner function and then the Jacobian of the outer function. I explained this once very explicit. Okay, so so how the Jacobian of the inner function, yeah, this goes from R, also the inner function, Jacobian of the inner function this is an n plus 1 cross 1 matrix. Yeah, because we go from R to Rn plus 1. Yeah, so it's an n plus 1. So what does this mean? This is typically a column vector. Yeah, and let's calculate this column vector. Here we have the function. We should differentiate with s. So what we do, it's just b and 1. Yeah? Here we have n components, b and 1 component. So it's a column vector here with, okay, and Jacobian of the outer function this is now vice versa. This is a 1 cross n plus 1 matrix. Matrix I should. Matrix. So it's a row vector. Yeah, and let's recall what is the outer function. This is u. So the row vector will be just gradient of u. Yeah, this is n components of x plus sb comma s plus t. And in the last component t we have just u dot of x plus sb comma t plus s. Okay, now let's insert this. So what we obtain, set prime of s. Now, first we should write this vector. Now as a row vector, du of x plus sb plus t plus s, u dot of x plus sb comma t plus s, and the whole thing times b1. Now if we do the calculation, we get, what do we get? We get b times gradient of u von x plus sb comma t plus s plus u dot of x plus sb comma t plus s. Okay, and since u is a solution, yeah, we really just recover our differential equation, evaluated along this trajectory, yeah, along this line. Yeah, so we get this expression along this line, but it's everywhere 0. So what we get, this is 0. Yeah? Okay, now you understand why we have chosen this trajectory in this way, because then we exactly get this. Yeah, this is the idea of the method of characteristic. Choose trajectories along which you can calculate the derivative with the help of the PDE. So it's constant. Yeah? So S going over to set of S is a constant function. And now, as you know from ODE, differential equations in general, this is also true for PDE, they have many solutions, infinitely many solutions. In general, differential equations, yeah, this is not only true for PDEs but general. Differential equations have infinitely many solutions. So there's an important question is, yeah, question, do there exists further conditions which uniquely determine the solution? Yeah, and from ODE theory, you know that initial value problems, yeah, this is the answer, initial values. So let's try to do the same. Try initial values. So this means we fix for t equals 0. Yeah, so we fix. Sorry, in this case we want to call it G. Fix, yeah, for all x in Rn. So what does this mean in our picture? Tx. Here we fix along this, if n is one-dimensional, then along this line, yeah, we fix values along this line or hyperplane in higher dimensions. Hyperplane. Here, yeah, the hyperplane where t is 0. Hyperplane Rn cross 0 sitting in Rn cross R. Okay, here we fix it. Now, we have our trajectory. We know it's constant. So we look for the intersection points, yeah? We look for intersection points, and then so does our general trajectory intersect this hyperplane? Yeah, and if it does, where it intersects? Oh, let's see. Yeah, we have the map S. Let's recall the map x plus is b, comma t plus s. Yeah, it intersects exactly if t plus s is 0, which is equivalent to s. Yeah, s is our variable. T t is given, so s is equal minus t. So at x minus tb comma 0. So here we have x minus tb at this point. And okay, now z is constant. What value we have? U of x minus tb 0 should be g of x minus tb 0. Sorry, no, for the g we don't have a second variable, it's only a function. Okay, so what do we obtain? U of xt is equal to g of x minus tb. This is the only possible solution. Only possible solution. And is it a solution? Think about. Is this a solution? What do we have to assume on G? If G is differentiable, then it is. Why? Now if we calculate d by dt minus b times gradient applied to g of x minus tb, what here if we take tb by the chain rule, this is minus b times gradient gradient g of x minus tb, and plus, this was our differential equation, and then plus b times gradient g of x minus tb. And this is of course 0. So it is, but if g is not differentiable, then there is no solution. Why? Because we derived that this is the only possible solution. But if g is not differentiable, then this is not a solution because it's not differentiable. So we see there is no solution. There is no solution if g is not differentiable. And in the next chapter, we will see that for more general functions g, that for more general that functions g, this is also a solution in a more general sense. And of course, since this is the only solution, it's natural to ask, maybe it is a solution in a more general sense. So here we see it's really worth to try to find generalizations of solutions, and all these generalizations, they will depend to define more general differentiable functions. Yeah, and this we will do in the next chapter. Yeah, so this is done in the next chapter. Okay, so this is now we have solved this initial value problem and understood that if G is differentiable, we get a unique solution. But if G is not differentiable, yeah, then we have no solution. Yeah, in this exercise in chapter 2, you will prove that for which more general functions it is a solution. Yeah, this will include all continuous functions and even all L1 functions. Yeah, for all L1 function, you will see that this is indeed a solution. Okay, so this is now we do we look for the inhomogeneous transport equation. Yeah. Please note, note that the transport equation is linear in the sense that the equation, the left-hand side, maybe I should say the left-hand side, that the left-hand side of the equation depends linearly on u. Yeah, here this is the left-hand side. Okay, and now completely similar to linear ODEs, there exists also an inhomogeneous version. Where we just add on the right-hand side some function which is given. So there exists an inhomogeneous version with given right-hand side f. This function f is now given. Okay, and now we will see that by the same method also applies to the corresponding initial value problem. So we have the same initial value problem. U dot, let us write this again once. Plus b times gradient of u of x plus xt is equal to f of xt. This is our equation, and the initial condition is we fix the values for all x in Rn. Okay, and we consider the same function. This is now our initial value problem. This we want to solve. Okay, and we do the same function. And then, okay, we take the derivative. Again, obtain this expression and see we get this. So this time it's not constant anymore, but it's given by the given function. So we can write this expression, this difference. This is of course the same as integrating from minus t to 0. So from minus t, at minus t it's this initial value, and at 0, if we insert here 0, s equals 0, then we have the point xt. Yeah? And so this difference is clearly this integral. We can insert here this integral, and here we just replace. This is just a simplification. Yeah, we call maybe s prime is equal to t plus s. Yeah, then ds prime is ds. T is fixed here. Yeah, and s is of course equal to s prime minus t. So by this substitution, yeah, here this should be s prime, yeah, then t plus s is replaced by s prime, and s prime minus t. So, yeah, so we get this formula. This is just a substitution, yeah, to come from here to here. This is nothing difficult. Okay, and now we obtain the following solution by this equation here. So we obtain this solution. And now note, yeah, very important. This form, the solution as a g plus x minus bt plus integral from 0 to t of f on x plus s minus t times b comma s ds is the sum of the homogeneous solution plus the integral over, yeah, and here if you look at t going to f on x plus s minus t times b comma s, this is of course the same as f, yeah, x plus sb minus tb comma s. Yeah, so if we observe these are which are the homogeneous solution of the initial value problems whose initial values are the inhomogeneity. Yeah, also this is, because this is of this form, so some function minus tb. So this is exactly a solution of the homogeneous. Yeah, and if we at t equals s, yeah, it's exactly, yeah, at t equal s, this cancels, so it's f on x plus s. Yeah, this is f on x comma s at t equals s. So the general initial value problem with the inhomogeneity means we look for the homogeneous solution whose value at t equal s is this function. Then and x, sorry, yeah, at yeah, when yeah, maybe we should write at oh no, it's fine, t equals s, yeah. And this is exactly the formula which you know from ODE. Yeah, this should remind you from ODE, from the ODE theory. Yeah? So in the same manner, we can solve the inhomogeneous equation. Yeah, we get the solution of the homogeneous initial value problem plus an integral over a family of solutions of the homogeneous initial value problems. Yeah. So yeah, this function here, yeah, if we insert, yeah, f of x plus sb minus tb comma s, yeah, for s equal t, yeah, what we obtain is equal to, yeah, and then we see f, then we get f of x, now this cancels t. Yeah, okay, so this is the initial value at is equal t and x, yeah, yeah, so the initial value. Okay, so in this sense, this is completely analogous to linear ODEs. Okay, so now let's recall what we have done today. What we have done today, we first give some overview over the whole lecture. Then we introduced what means partial differential equations. We introduced some notation. And then we came to the first simple examples, the homogeneous transport equation. Yeah. We solved it by the method of characteristic, and then we understood how the same methods applies also to the inhomogeneous transport equation. Okay, thank you.